As been mentioned here in this spark.apache.org, runs programs up to 100 times faster than Hadoop MapReduce in the memory and 10 times faster on the disk. How your Spark programs able to achieve this performance gain, and how this in-memory computing is going to improve the efficiency of your computing. Before I move on to all those technical details, let me start my discussion with, I need not tell you what this slide indicates. You know very well the data exists only in one of these three forms. There is no other possibility. Your data could be structured. That is what I say, the schema first. You define the schema first, then you start storing the data. That is where we call this as structured. The other name for structured data is schema first. Semi-structured is schema later. And unstructured is schema never. I tried my best to depict here relational databases, your XML documents, and your tagged text or media, your plain text. So as your data exists in one of these three forms, you should have a way to process. That is where you start your discussion on big data with three V's. I don't want to go back to that stage and discuss that one. But big data is anything which has got three essential characteristics: volume, velocity, and your variety are the three V's with which we define something called big data. Volume and variety are linked with your storage, and your velocity is linked with your processing. So your three V's are being addressed well with the help of, that is what big data is basically. Most of the times people think big data is a platform or a technology. No, big data is basically a problem statement. Big data is basically a problem statement. That is what we call it as three V's. You have something called volume, variety, and velocity. Your volume and variety are linked with your storage. That is, when you have huge volume of data, where you store that? When you have wide varieties of data, where you store that? So these two are linked up with your storage, and your volume and variety are going to throw a question or a challenge to you. Huge volume of data, where you store? Wide varieties of data, you may ask how you store or where you store. So your volume and variety throw a challenge related to storage, and your velocity throws a challenge towards processing. I mean, the rate at which the data is coming into your box, at the same rate, if you are not able to process, you will not be able to share results with the end user properly. So at what rate the data is coming into your box, at the same rate you should be able to process. That is why we are calling this as the problem related to processing. The previous two are related to your storage. And these two challenges are well addressed using something called Hadoop, which implicitly called as HDFS and MapReduce. Your storage problem is addressed using HDFS. Your processing problem is addressed using your MapReduce. That is why Hadoop is considered to be an open source solution to the problem called big data. So big data is basically a problem statement To this problem statement, the solution is given in the form of Hadoop. I don't know what is the view you have, friends, but believe me, big data, the term big data is a regular term on the internet. You go and search anywhere, you find the term called big data. Very next to big data, you also find the term called Hadoop. Most of the time people, they think or they interchange these two terms. Nothing wrong that you use these two interchanged, but big data is definitely not a technology, definitely not a platform. Big data is basically a problem statement. To this problem statement, the solution is Hadoop. Now, using your MapReduce, you are processing the data. But this processing is absolutely fine when it is your batch mode. But especially when you want to process some data iteratively, same data you want to crunch it with the different algorithms, and you want to process that one by extracting the data in an iterative mode, then your MapReduce is going to fail. That is where the term called DAG comes into picture. I don't know what is your perspective towards this one. Directed acyclical graph. That is what we mean by DAG, directed acyclical graph. We talk about this one. When we have a DAG of jobs, and if the jobs are implemented using MapReduce directly or indirectly, because when I say a DAG, it necessarily need not be MapReduce all the times. You can have a MapReduce job, then you have a pig script, then you have a high query. All put together we call it as a DAG, because you write your MapReduce directly as a MapReduce or indirectly as a pig script or a hive query, but all directly or indirectly your MapReduce only. You have one MapReduce job here, one more MapReduce job, and one more MapReduce job. You start here and keep moving, we end here. This is not a cyclical. Cyclical is something like we start here, move towards, and finally we end up here. This is called cyclical. And we start somewhere, we keep moving in a directed fashion. That is called acyclical. And this is moreover directed. It is clearly been mentioned from here to here, from here to here, and this is where we end. That is where we call this as a DAG. So especially when we have a DAG of jobs implemented using your MapReduce, you have a lot of bottlenecks. But even you work with your MapReduce or you work with your Spark, one thing that you need to understand, have a look at this one. This is what your Hadoop ecosystem is. At the very lowest level, we have something called data storage. And on the top, you have data processing. And on the top, you have data access. So if you look closely, if you use Hive to process the data present on HDFS, we are going to make use of Hadoop MapReduce framework only. That is the reason why I mentioned this data access layer on the top of your data processing. I think you notice that clearly here. Your data access is a layer on the top of data processing. And we have data management on the top of data access in the form of Uzi, Flume, Zookeeper and all. And you have data analytics at the final level with which you are going to analyze the data which is present on your HDFS. Data analytics on the top of your data management. This is what you call it as Hadoop ecosystem. The thick Hadoop ecosystem that is built the last roughly a decade, I say, but not exactly a decade, at least the last 8-9 years, the advent of the Hadoop to this modern world, how the data crunching has been changed altogether, especially for the last 4 to 5 years, Hadoop became a de facto in crunching your big data. The same, when you come to this modern architecture now, you can see this is called data analytics stack that is proposed by Berkeley. You look at the same thing. Please friends, try to observe this one, this stack and even this stack. You look at this one closely. At the core level, we have the same. You see resource virtualization in the form of Mesos or Hadoop Yarn and storage in one of these forms. And processing engine now is going to be your Spark. That is what we need to understand, friends. Yes. On the top of your Spark core, that is a processing engine, we have data access, your access and interfaces. And on the top of this one, you may have your, your other tools to access the data or to analyze the data. You try to compare both. You'll be able to understand. I want you to comment on this one, friends. This is what your MapReduce based big data analytics stack. MapReduce based. And this is Spark based data analytics stack. You try to compare both, you'll be able to understand the fundamental difference here. The fundamental difference here. I want you to comment on this one, friends, please. Jayanta.
Yeah, um, difference in the sense, like as I said, MapReduce are like on disk mainly, and Spark is in memory. So basically here we will do a lot of streaming real time. Basically it's that's a batch, and this is real time streaming.
Wonderful. So you see both, you work either with this modern stack, what I'm showing you now, or you work with your earlier. One thing that you can find clearly, storage is the same HDFS. Maybe layers of abstraction on HDFS, but it is HDFS only. So what is getting changed here? Your processing engine is getting changed. So you have your MapReduce there and you have your Spark now. And on the top you have your access interfaces in the form of streaming, SQL, R, varieties of interfaces are coming on the top. Like how on the top of your MapReduce you got Hive, Pig, Scoop, Avro, Mahout, all these are the layers of abstraction on the top of your MapReduce. You have the layers of abstraction on the top of Spark, that is called Spark Core. Spark SQL, Spark Streaming, Spark R, Graphics, Splash, MLib, there is a machine learning library, MLib, that is what we call it to be MLib, a machine learning library. So all these are the interfaces built on the top of your Spark core. That is what the processing engine. The processing engine in this is your MapReduce framework, and the processing engine here is now. Why I am showing you so clearly this one is to make you to understand, because of the change in the processing engine from your MapReduce to Spark, what advantage we get. What advantage we get. So let me have a clear discussion on this. I really don't know what is your observation towards MapReduce, friends. But when you submit a MapReduce job, that is where we expect some basics of Hadoop to take up your Spark and Scala. So I expect all of you to have some basics or foundation on MapReduce. So taking that into consideration, I am discussing this one, friends. How you submit your MapReduce job? Hadoop is there and you specify maybe the path where your jar file is present. Once Hadoop jar, and I specify the path. Path, I mean, say maybe work, I have MR jobs, and I have my jobs.jar. This is what the jar file that is present on your local file system. This is what your local file system. And I'm going to specify here job name, that is my job. That is a job name. This is what your job name. And then I'm going to specify the path /tmp /sandbox /abc.txt. This is what we call it to be input path. And I specify /tmp /sandbox /abc_out. This is what I call it to be output path. If you look at this one closely, Hadoop jar, because using Hadoop, I also can specify Hadoop FS to navigate the file system. Same like in the place of FS, we specify jar, Hadoop jar, Hadoop jar. So my intention is to run the jar file. So I need to tell where my jar file is located. My jar file is located here. In that jar file, there could be number of jobs, which job you want to run. When the job is running, I need to tell from where it needs to fetch the data. And when the job is running, finally where the output needs to be stored, that also I specify. This is how I run my MapReduce job. Hope you are clear with this one. The moment I submit the job to my job tracker, this is what the client, when the job is being submitted, your job tracker is going to receive the job and talk to the name node immediately, saying the file called abc.txt, where it is located and how many blocks are there and where those blocks are present. So when your job tracker is going to communicate with the name node is going to reply saying, hey, the file called abc.txt has got 4 blocks and those 4 blocks are present on these nodes. Maybe node 1, node 5 and node 9 are the 3 nodes on which, so immediately what the job tracker will do is same .jar file, I send it to my node 1, same .jar file, I send it to node 5 and same .jar file, I send it to my node 9. It will not send to all the 100 nodes present in your Hadoop cluster. It will send only to those nodes where your blocks for the given data set are present. Where they are present? They are present on your node 1, node 5 and node 9. So your job tracker will push this jar file only to those nodes where your data is present. This is what we technically call it to be push the code to the place where the data is residing. So this technique is called push the code. And the other technique regularly what we implement is pull the data. This is suitable when your data is limited. When your data is limited, nothing wrong that you pull the data. But when you're talking in terms of big data, as it is not possible for you to pull the data, what we are doing is pushing the code to the place where your data is present so that we can take the advantage of data locality. Wonderful, friends. So we have submitted the job to the cluster. When we submitted the job to the cluster, I need not tell you how the job execution is going to happen. The first and the foremost thing that is been identified is input format of the job is been identified. Input format. Based on the input format only, I'm going to identify how many splits are needed for this particular data set, to process the data. How many splits? I come to know that one only. Let me also take you to have a look at this diagram, friends, closely. This is what the life cycle of your MapReduce job. I mentioned just now, this is my HDFS. You see that one, friends, closely here. On my HDFS, the file is present, nothing but the data set. Based on the input format, splits are being identified. Each split is expected to be processed by one mapper. Please observe this one, friends. Then you will be able to clearly understand what is the advantage of your in-memory computing compared to your MapReduce part. Each split is assigned to be processed by one mapper. With the help of the record reader, I read the records from the split and give it to my map or map function as key value pairs. Record reader is going to read the data from the split in the form of a record and split that into key value pair and then give it to your mapper. I mean map function. So your map function is going to receive the key value pair, process the key value pair, and temporarily store these things on your local disk. This is my node 1. This is my node 1. Your intermediate key value pairs are not being stored on HDFS. Can you tell me, friends, why the intermediate key value pairs? I mean, the output of your map function. I'm going to tell you here. Your map function is going to take key value and the third argument is called, your context object, and your map function takes key and value as an input. What output it produces? What output it produces, friends? It produces key value only again. You take any MapReduce job, word count MapReduce Java, if you take that one, you take any MapReduce job, you look at that one closely, you see here, what your map takes key and value, and what they do, context dot write of key and value again. They take key value, they give key value. That is what you need to understand here. So your map function takes key and value and produces key value. Now the question here is, the key values that are produced by the map function, where they are going to be stored? They are not going to be stored on HDFS. Can any of you tell me, friends, why the intermediate key value pairs are not stored on the HDFS? They are stored on the local file system. Friends, this is not to question you. This is only to get the inputs from your end. Based on that, it will be easy for me to drive further. Can any of you tell me why your intermediate key value pairs are not stored on HDFS? Why they are stored on the local file system?
So we see, okay. So this is, we are saying it's intermediate, right? That's not the end output.
Yeah.
So the HDFS will have only the that end output. So this is where the intermediate value we need for further process.
Yeah.
So that's what we are using local resource. So that will be like all that, like memory, IO, CPU, everything will be used local to that node, data node.
Wonderful.
That's what we call, yeah, that's what we call this work node.
But the main reason behind Jayanta is
Actually, reducer will execute after the map task gets over something.
yes, right. I agree with all of you. But the main reason is anything you write it on to HDFS, should obey the replication factor set by you at the cluster level.
Oh yeah, absolutely.
So anything that you store on the HDFS must obey the replication factor you set at the cluster level. So you write something to the cluster or HDFS. What happens, friends? It should get replicated. It should get replicated, and that is not the final data. That is only the intermediate data. Then after some time, I need to remove, writing it to HDFS, getting it replicated, and removing it, and it's all going to be a painful job. That is the reason why I write the intermediate data to the local file system. So what you need to understand here, the output of your map function is a key value pair written to local file system. So there is one read from HDFS. There is one read from HDFS, and after map phase there is one write. You agree with me, friends? And in this diagram you observe closely, the output of all the map, because there are 3 splits on this node for the given data set, so 3 mappers will be functioning. So the outputs of 3 mappers being written to the local file system. Now usually this output, whatever been written here, is going to be read by the combiner. You agree with my point, friends? We have shown partitioner there directly, but we will be having a combiner in between your mapper and the partitioner. So combiner is going to read, because 3, how many are there here now? 3 mappers are there. So 3 intermediate outputs are being stored, each from, this is mapper 1, mapper 2, and mapper 3. So the output of all the 3 mappers is going to be read by the combiner and finally produce some output by consolidating all these 3. So there is one more write again. So what is there? There is one more write again. And this write is been again read by your partitioner. Why? Why? I'll tell you one thing. See here, friends. This is my mapper 1. It produces A1, E is 1, D 1, all 1, like this. My mapper 2, again A1, all 1, D 1. And my mapper 3, A1, E is 1, and D 1. Now, this is the thing what I am showing you here, this one. And this is the one which I am showing you here, the second one. And this is the one which is the third one. Now, instead of me transporting all these key value pairs in the network, what I do is, with the help of my combiner, I make it as A3. This story is happening only from node 1. I have one more thing called node 2. The role of the combiner is called local aggregator. The role of the combiner is local aggregation. So A3 and is 2, then all 2. I hope you are following with me, friends, what I am sharing here. That is being done by the combiner. Now, what is done by the combiner is read by the partitioner, and partitioner is going to decide which key value which key value should go to which reducer. The partitioner will only decide. The partitioner will only decide which key value should go to which reducer. But the actual transportation is being done by shuffle phase. Shuffle is going to actually transport. Your partitioner will only decide which key value pair should go to which reducer. But the actual transportation is done by the shuffle phase. So there is something called network IO involved during shuffle phase. And after shuffle, there is something called sort, which is going to be done on the fly and finally being given to reducer. Reducer finally writes it to HDFS. Now if you observe closely, in between map and reduce, you just see how many read writes are happening. How many read writes are happening? There is one write after map and one read to the combiner, one write from the combiner and one read by the partitioner, and one network IO, and finally a written to the HDFS. One read from HDFS, one write to HDFS, and in between two reads and two writes and one network IO is involved. You know very well, the biggest challenge is always IO, which has got latency because of the limitation of the hardware, not because of the limitation of the computing, limitation of the hardware. Because my read-write arms, I cannot make my read-write arms to move such fast, they generate sparks. I cannot move at that speed. I need to make sure my read-write arm is going to move at a speed which will not damage that easily. Beyond that, if I make my read-write arm to move, then it may cause any damage. My hard drives are going to undergo wear and tear, and for every 2 days or 10 days or 1 month I need to change my hard drives, which is practically not possible. So I may be interested to move the read-write arm so fast, but practically it is not possible because the limitation of the hardware. That is the reason why these days you are seeing slowly your hard drives are replaced with solid state drives and being slowly replaced with your flash memories. That is what the improvement happening. But these are expensive at this stage, but they become more affordable. Then your computing is going to become much more faster. Your computing is going to be much more faster when your storage on solid state drives or on the flash memory is going to become affordable. Then your processing is going to be much more efficient. But at this stage, at least it is a disk IO, because the latency in the disk IO, you have all the issues in terms of processing, but not because of the core processing that is being. That is what I am trying to show you here in this diagram. Please look at this one, friends. On node 1, I have 3 splits for the given data set. Based on the input format, the splits are being identified. Each split is processed by one mapper with the help of the record reader. When records from the split are being processed completely, yes is OR, then the output of all the mappers on the local are consolidated using your combiner, which is not shown in the diagram. And after the combiner phase, the partitioner phase comes into picture to decide or mark which key value pair should go to which reducer. Your partitioner only marks which key value should go to which reducer, but the actual transportation is going to be done by the shuffle process, and finally before the key value pairs are given to the reducer, they are being sorted. That is why usually the output you see from the reducer is always in the sorted order. I don't know whether you notice that anytime or not. You want to go back to your MapReduce, submit one job and see the output of the reducer in the part R file, you always see in the sorted order, because The key value pairs are being sorted before being given to the reducer. So now this thing, because of the IO involved here, have a look at this one. If it is a case of a single map reduce job, if it is a case of single map reduce job, one map reduce job, I have explained you before. But if it is the same DAG, then what is going to happen? Please friends, I want you to actively participate here. If it is a single map reduce job, we have seen what is the IO involved. If it is a DAG, I mean there is one map reduce job. After finishing this one, there is one more map reduce job. After finishing this one, there is one more map reduce job. This is what we technically call it to be a DAG. That is what we achieve using your UZI. Okay. Now I ask you, of course, this necessarily need not be a map reduce job. This could be a pig script. But how it runs in the very deeper level, it runs as a map reduce job only. That is why pig is technically called as higher level of abstraction on the top of map reduce. And this could be your Hive query. But again, superficially it looks like a Hive query, but at the very deeper level it is a map reduce job. Now, for this map reduce job, HDFS read and this is HDFS write. To this map reduce job, HDFS read, HDFS write. For this map reduce job, HDFS read and HDFS write. So for this DAG, there is one read, and I mean read nothing but input, and finally you have the output. But in between you see everywhere we have, and within every map reduce job there is IO involved, what I have explained you before. So how massive and complex this becomes. Are you able to understand this one, friends?
Yes, yes. Yeah.
Now look at this one. Input, read from HDFS and write it to HDFS. Read from HDFS, write it to HDFS. Read from HDFS, write it to HDFS. That is what your DAG is. But the same when you come to your Spark. I only read, observe this one closely, friends. If you are able to understand this one, you really appreciate, oh, wonderful. That is the reason why Spark is, you yourself will confirm. You don't need any proofs, friends. You don't need any documentation. You don't need any advice from anyone to confirm that Spark is no doubt powerful than MapReduce. But Spark may not be the suitable or the right candidate for every kind of data processing. We cannot use Spark for every kind of data processing because of its expensive nature in terms of the resources. And that is where I want to say it very clearly to you. Your MapReduce can never be replaced by Spark. Spark will have its own advantage and usage. MapReduce has got its own advantage and usage. Both are going to coexist on the same cluster. You have the cluster. On the cluster, you have both MapReduce and Spark which coexist. One is not going to replace the other. This is what I want you to clearly understand, friends. And I want you to clearly get the knowledge. It is not that one is going to replace the other. That never happens. Maybe MapReduce is being made more robust, more efficient time to time, trying to move towards Spark because of the advancement in the hardware and the processing logic and the efficiency of improving the read mechanism and the write mechanism. And Spark still progress with the advantage of your more storage techniques. I'm talking about the in-memory techniques. So these two are going to have their own life cycle in terms of their development. So both are progressing towards the best. So one is not going to replace the other, at least in the very near future. Maybe over a period of time, when I have my solid state drives and the flash memories more affordable, I don't need even to have the map reduce kind of techniques. I can replace the entire batch processing with my in-memory computing. So that day is not far ahead, but at least till then, your MapReduce is going to coexist with your Spark on the same cluster. One is not going to replace the other. But now, look at this slide very closely. You yourself can confirm it. You need not depend on me. What is that happening? In the Spark case, you have one read from HDFS, and ultimately, for the entire DAG, there is one write to the HDFS. So when there is only one read from HDFS and one write to the HDFS, not only the read writes of the HDFS been eliminated within the MapReduce job, there is IO that also is being eliminated. And I need not tell you, because of this what happens. Are you able to understand my point, Ramji here, Jayanta?
Yeah, yes, sir.
So now I think you are confident to say how your Spark is going to be efficient compared to, I want you to understand this one, friends. And you may ask me one thing, hey Srinivas, why I do the iteration? I clearly mentioned just now, in computing, we always go with a DAG. That is the reason why Uzi is in picture. We never work with one single MapReduce job. Of course, as a developer, you are going to develop a MapReduce job, a single MapReduce job, and that single MapReduce job is going to perform some small tasks, but not the entire thing. That is connected to the next MapReduce job, directly or indirectly. It could be a MapReduce job, or it could be your pig script, or a Hive query, or a scoop command to import or export the data, whatever it is. But ultimately, all are being drilled down to the MapReduce only. So the reads from HDFS been straight away eliminated. So when you come to Spark, how many reads are there from HDFS? Only one time read and finally one time write. In between, everything is stored in the memory. That is why it is been shown very clearly in this diagram, these memory chips. The read writes happening at your MapReduce and the read writes happening at your Spark. You see that one closely here. So because of this, what happens? Your HDFS reads and writes are being eliminated in the entire DAG. If my DAG has got 4 jobs internally, how many read writes I was able to eliminate? 3 read writes I was able to eliminate, because one definitely needs to be done. You cannot eliminate that. You have definitely one read from HDFS, one write to HDFS. That cannot be eliminated. But in between, the reads and writes can be eliminated by keeping the data in the primary memory. I mean in the RAM. Now you see this one. This is what the beauty part here. That is the reason why I said 10 times, 200 times faster than network and disk. And why they have given that range? Tell me. 10 to 100 times. That is what the most crucial thing, friends. 99% of the people who already know Spark, they are also not able to clearly say what is this range of 10 to 100 times faster than network and disk. Is because of the reason If it is your, look at this one closely, friends. If it is one MapReduce job and one Spark transformation or action, then you see read from where? HDFS, and write to HDFS. Even in Spark, if there is only one transformation or action, there is definitely a read from HDFS and finally to HDFS. Your write to HDFS. So in that case, your MapReduce job and the Spark job, no difference. But the difference comes is within the MapReduce job, there is IO involved. Local spilling, from there reading, that all is been eliminated even inside a single Spark action or a transformation. That is the reason why I was able to achieve 10 times faster, because the local read write and the network IO what is involved is being eliminated. Because of the local read write and the network IO, my Spark job is 10 times faster. I see more benefit only in the case of a DAG. Only in the case of a DAG. If it is a simple single MapReduce job and a single Spark action or transformation, you will see only 10 times faster. Because within that job, you have what you have? The local disk IO and the network IO involved within one single MapReduce, that is being compensated with in-memory, and as a result you have only little performance gain. That local spilling now can be taken out, that network IO can be taken out, because it is all happening in the main memory itself. But the real advantage of your processing will be observed only in terms of a DAG. And you know very well, so there is no single occasion in the real environment where you run only a single MapReduce job to process your data. That is very rare. You always has got DAG, especially when I come to machine learning. Which is the active domain of the entire big data space, which is a predominant domain of the big data space, machine learning. And this is what the actual usage of your big data. In the machine learning, if you see, I will use iterative processing. What I mean by iterative processing? I process the same data with different dimensions or different parameters. That is what I call it to be iterative processing. So iterative processing is the essential thing for any machine learning. That is where your Spark comes into picture with its efficiency. But for a normal simple job, what I've explained you here, there will not be much performance gain compared to that of your MapReduce and your Spark. Definitely one HDFS read and one HDFS write is required in MapReduce or even in Spark. Within that job, the IO involved can be eliminated. That way I gain 10 times faster compared to that of your traditional MapReduce. Friends, I want you to confirm this one. I don't know what is your feel towards this, but I want you to confirm this before we move ahead talking anything about the Spark. Are you able to understand, Darshil? Jayanta?
Yes, sir. Yeah.
So you got the basic understanding. That is the reason why Spark is becoming a de facto for your data crunching at a sensitive level, not for every occasion, only at a sensitive level. So I want you to really feel that one, friends. I mean, on your own. Maybe my explanation might have given you some understanding, but I want you to get that feel on your own. And maybe my explanation might have given you some big picture, but I want you to go back and work on this one and try to understand in what way my MapReduce. I don't want to degrade MapReduce here, because MapReduce has got its own advantage and its own importance as part of your big data landscape or your Hadoop ecosystem. But when it comes to data processing, you require on the fly, almost like, data coming in and going out, coming in and going out. When you require the data processing to happen at a lightning speed, then MapReduce may not be the suitable candidate. And in that case, especially when we talk about machine learning, your iterative processing demands the resources, and that can be provided only by your Spark. That is where I'm trying to make you to understand here, friends. Look at this one. 10 to 100 times faster than network and disk. But they're not saying it is 100 times faster all the times. No, it is not 100 times faster, because if it is not a DAG, then you will be able to see only that performance difference what you see as part of the local disk spilling, what I'm trying to show you in this diagram. That is the reason why, in order to understand Spark, we need to first understand MapReduce thoroughly. Our knowledge on MapReduce only gives the strong foundation for your Spark. What we are not able to achieve there, that we achieve in Spark. So that is the reason why I initiated my discussion with MapReduce. The more you understand there, the more easier we only learn things, how we can, that is the reason why, MapReduce is a definite thing to take up your Spark programming or the Spark level of implementation to crunch your big data. And that is viable or possible. You can see that very clearly here. The intermediate output of mapper is stored to the local disk. That is avoided when you come to Spark. And reading from your local file system by the combiner and write it to the local file system again, that read and write also been avoided. If that read and write is been avoided, reading by the partitioner is also been avoided. And partitioner been avoided, then my network IO is been avoided. And finally, there is only one read from HDFS and one write to the HDFS. All intermediate happens through in memory, within the memory. And that is going to improve it, because reading the data from disk is the most expensive thing compared to the processing, because your processor can process at a great speed, which is far above your reading and writing capacity on the disk. Say I read 10 bytes, imagine, I'm not telling, 10 bytes per tick or per clock. My processor can process 10 into 10,000 times what you're reading from the disk. If my processor is not getting sufficient inputs to process because of the IO limitation, what is the use of having great computing with me? Even though if I have great computing, if my computing is not getting enough inputs to process, then what is the point of having great computing? Even though I have great computing, it is of no use to me if I am not able to get the necessary inputs to process the data. That is the reason why this disk latency is the biggest bottleneck to the big data space. I am expecting in the very near future, this is going to be replaced, slowly going to be replaced with your solid state drives and your flash memories. Now at this stage, because of the technology and the R&D that has been done on that one, its cost is a bit high. But over a period of time, like how now you get a 1 terabyte of RAM at an affordable price. 1 terabyte of RAM at an affordable price. But sometime back, 1 TB of hard drive is expensive. But now 1 TB of RAM is also affordable. So servers having multiple terabytes of RAMs is a quite common thing these days. It is not a rare thing. Servers having multiple terabytes of RAM. I'm not talking about multiple terabytes of hard drive. Multiple terabytes of RAM is not an abnormal thing these days. So because of the advancement in the hardware and the hardware becoming cheap day by day, because of the technology advancement, my storage is going to become more affordable and economical, and I'm able to retrieve the data fast. The more I retrieve the data fast, my processing can be accelerated. That is what is happening with your Spark, nothing more than that. Because your primary memory is definitely faster than your secondary memory. Reading or writing to the primary memory is different than your reading writing to your secondary memory, I mean your hard drive. Only that limitation is bringing the biggest difference, and rest is when you're doing your iterative processing and all your IO being avoided, as a result definitely your performance gain is there. Other than that, your Spark doesn't have any specialty in terms of its processing. It uses the same CPU. What time your MapReduce job takes to actually process your data, even when you come to Spark, maybe slight difference you find because of the change in the libraries and the languages that you are using and the availability and the code that we write. Actually, the tons and tons of code you write in MapReduce to crunch the data is being abstracted when you come to your Spark. As a result, a slight performance gain may happen, but the actual performance gain is happening because of eliminating this disk IO. I appreciate, friends, I appreciate if you are able to understand this one, and that is what the base for your Spark, and that is why you see this one. On the Spark core, we have the other layers, like how I've shown you before. You can clearly understand that one, friends, here. How your ecosystem is. Your ecosystem has got, I think I've shown you that one in the same. Yes, the ecosystem here is like this. How your MapReduce has formed a base for your Hive, Pig, Scoop and all. Now your MapReduce, your Spark core is going to become a base for your Spark SQL. How you have your SQL on your MapReduce, you have Spark SQL now. That is called MapReduce SQL, called as HiveQL. Spark streaming, the MLlib, that is called machine learning library, GraphX for processing your data stored on graph databases. For all those things, you have your Spark core. Spark core is a base, and for this Spark core, you have the abstractions in terms of your, I don't know whether you heard any time about this or not, but if you heard, definitely you can appreciate this one. Are you clear with whatever been discussed till now? You have any questions to me, friends? I want to wipe out this this blackboard and get the other one. If no questions, I move further. You see something called, this is one more important and the crucial thing as part of your Spark that needs to be understood by you. That is RDD. If you understand this concept of RDD, most of the complex things associated with your Spark are being well addressed. RDD. I think definitely you might have heard about this one. This is called resilient distributed data set, RDD. Let us start with the data set. I need not tell you what is data set. Data set is nothing but a file or data on HDFS or similar storage. It necessarily need not be HDFS all the times, because slowly the storage techniques are also getting transformed. They are also getting changed. Okay. So I have my file which is of 8 TB. Definitely not possible that I store this 8 TB file on one primary memory slot. It's not possible. I cannot have one 8 TB. Even if I have 8 TB, then storing the data. 1 second. So even if you have 8 TB of RAM on one node, I cannot pull the data from different nodes and put it in this RAM. Not possible. That is the reason why this data set is now distributed. Say for example, this is a node on which I have few blocks belong to my data set. There is one more node where I have few more blocks. This node, my data set related blocks are not present. This node, no blocks, and this node, another 2 blocks. So only these 3 blocks will be stored in the primary memory, I mean RAM of this node, and these 3 blocks in the RAM of this node, and these 2 blocks in the RAM of this node. Now tell me, your data set itself is now distributed across machines. It is available on different RAMs. That is what I am trying to depict here. In this you can see that here. What is that? The diagram indicates. See the diagram here. Diagram indicates very clearly your data set is distributed. Your data set is distributed. It is not centralized anymore. I mean, all your data present on the RAM of a specific machine. No, not required. You can still use the concept of data locality. You can still utilize the concept of data locality. Where your data is present, I read and put it in the RAM of the same node. So I need not move this to a different node through the network. Again, your IO is involved there. That is why I'm not doing that. That is where I'm saying read from HDFS and form a distributed data set. This distributed data set is related to your primary memory. And why we call this as resilient? For the reason, for any reason, if one partition, like how you have splits. Let us talk about partitions in more detail at the later stage as part of the course, friends. So like how we have a split at MapReduce, we have partition at a Spark level. Both are the same. At MapReduce, we call it as a split. At Spark level, we call it as a partition. For any reason, if one partition is lost, we need not worry. Only that partition can be rebuilt. The information required to rebuild that partition is present within the dataset itself. That is why we are calling that as resilient. Even in the event of your partition failure, or we lose some partition, because when we are doing processing at a large scale, one partition getting lost is not an abnormal thing, whatever the reason. Hardware failure, RAM failure, whatever the reason. If one partition is lost, I need not worry. Only that partition can be rebuilt without disturbing the entire distributed data set. That is what the beauty of your RDD. That is the reason why we are using the term called R here, resilient distributed data set. The distributed data set with the fault tolerance. We have fault tolerance even when we go to MapReduce. We have fault tolerance when we go to your HDFS. Fault tolerance is there everywhere. The same fault tolerance when it comes to your Spark, we are calling it as resilient. The information required to generate this partition is present within the data set itself. So that in the event of your partition, missing of the partition, or you lose the partition, never mind, you can build that partition very comfortably without any problem with the information present within the data set. That is why we call this as a, not as a distributed data set, not just as a distributed data set, it is a resilient distributed data set. What is a resilient distributed data set? A distributed data set with the mechanism to build the partition on its own at times when we lose the partitions. That is what the beauty part of your RDD. And RDD is the base or the foundation for your Spark. RDD is a building block for your Spark programming. So with these RDDs, you are able to process the data in the memory without touching your IO, local storage, or even in terms of your network. And that makes your Spark to be more efficient and powerful. I believe, friends, you are able to understand what is RDD. A distributed data set with a fault tolerance is called a resilient. Even in the event of your partition, you lose a partition, you have 10,000 partitions. One partition been lost. Are you going to throw away and reconstruct your entire distributed data set? That is ridiculous. That is the reason why these distributed data sets are developed with a fault tolerance. So a partition which is lost can be rebuilt with the information present within the data set itself. That's what the most, the beautiful aspect of your, and you go and check it out, friends. This is what the original, let me show you that. One second, Spark. We have something that's not an issue. You can get it from online. That is Spark. That is something called. So this is actual, the research paper submitted by these people as part of the research, University of California, Berkeley. Spark. Cluster computing with working sets. You see this one, they say here very clearly, resilient distributed data sets is a read-only collection of objects partitioned across set of machines that can be rebuilt if a partition is lost. This is what Spark program or provides two main abstractions for parallel programming: resilient distributed data sets and parallel operations. That is what the entire story is. You see this one, I don't know whether you are getting this one or not, friends. See here. Spark provides two main abstractions for parallel programming. One is RDD and the other one is parallel operations on datasets invoked by passing a function to plan the dataset. And in addition to this one, we have two more things, shared variables. And you see this one here, what an RDD is. Is a read-only collection of objects partitioned across a set of machines that can be rebuilt if a partition is lost. That is what the most beautiful thing, friends. Are you able to understand what I'm saying here? Jayanta, Darshil, Ramji.
Yes, so sir. Here, what do you mean by partition? Is that same like a replication?
No, not replication. No. Replication
No. I got the partition part. I got it.
Yeah.
But that it says that across set of machines that can be rebuilt, it's partition loss. But what does it mean that it's across? Is a partition being created in across?
That is what we discussed here, right? Now, your partitions are not present only on one node. Your few partitions are there on this node, few partitions are there on this node, and few partitions are there on this node.
That's what I'm saying, that same partition being present in multiple nodes, so that there not be possibility of losing data.
You are mistaken. If same partition is present, it is called data replication or partition replication.
Okay, yeah, no, that's what I'm not getting that part.
When partition replication is there, where is the concept of you losing a partition? If one partition is lost, other partition is available. You imagine how much expensive it will be if replication of the partition needs to happen in the main memory.
Yeah, that's what I'm thinking. Then what does it mean that partition across the multiple machines?
That is where I mentioned here. We have a split here, right? Based on the input format, your dataset is divided into splits. Same concept of split. When it comes to your Spark programming, we call it as a partition.
Okay. Here the split happening in one machine, their partition being, it's happening in multiple machines on memory, right?
No, splits are there on multiple machines, right? You have few splits here or you have few splits here. On node 2, we have splits, right? Again, on node 3 also we have splits.
Same. So that's what I'm saying. This is the same thing, but it's on in memory.
Exactly. This is a split that is there on the. Split is basically, I don't know what is your understanding towards split, but as you specifically raise this one, let me take the privilege of discussing that split also with you so that you'll be able to understand. There are two things actually here. One is the split and the other one is a block. See here? Block is the physical storage on your hard drive.
That's true, yeah.
But split is a logical division of the data based on the number of records. You see, block boundary, in this diagram you see closely, block boundary from first record till the middle or some part of the fifth record is a block boundary. It never bothers. It never bothers. It only bothers 64 MB data is there or not. Is there? It is a block. But when it comes to the processing, I cannot process 4.5 records or 5.5 records like that. I can process either 5 records or 4 records, but not 4.5 records. That is why I do one more logical division of the data called as split. Same split when we come to Spark, we call it as partition.
Oh, got it. Okay.
That's the reason why I say our strength in MapReduce is a foundation for your Spark programming. There is no difference between MapReduce programming and the Spark programming, only the terminology different. And instead of we working with the a secondary storage, we work with the primary storage, but in terms of a developer, it makes no difference. Only thing is we need to learn the transformations and the actions. That is what I'm trying to show you here. You have, what are the two things? Parallel operations. You see that one here, parallel operations. You also see this provides you two things, which I'm going to show you here. Give me a minute. You'll be having two things called transformations and actions. Transformations and actions are the two things with which you are able to perform your entire activity. So you are going to have transformations and actions in terms of somewhere here you'll be seeing. Yes. You see this one? RDDs achieve fault tolerance through the notion of lineage. If a partition is of a RDD is lost, the RDD has enough information about how it was derived from the other RDDs to be able to rebuild just that partition. I hope you are getting the point.
Yeah.
And you also see here, nothing wrong that we search for that. Actions. Transformations. Yes, here. You can see by changing by 1 second. It should be in the same document. And that's not a problem. Yes. 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 RDDs are going to support two types of operations. Transformations, which can create a new data set from an existing one, and actions which return a value to the driver program after a computation on the data set happens. So your RDDs are going to support two types of operations. What those are? Transformations, which transform your data set from one to the other, or with the help of transformations, we can transform the data set from one format to the other format, or one style to the other style, or one shape to the other shape. And the other one, actions, which are going to give you, you know very well, for every action there will be a result. With these actions, you are going to get the result by running that action on the RDD. You are able to get the computation. Say for example, you want to find out the number of records, you want to find the word count, you want to find these kind of things, you apply actions. You want to transform your RDD, I mean you want to abstract the data or filter the data from one RDD, you can generate one more RDD. Those kind of things can be done using your transformations. So these are the two main abstractions on the RDD with which you are able to achieve your goal of the same MapReduce what we did earlier. What we are doing with your peak, what we are doing with your high, all can be done even with your RDD with the help of your transformations and actions. The beauty part here is these transformations and actions are being induced into the library so that they can be readily used by you instead of you writing. I don't want to degrade MapReduce here, but believe me friends, let me take you to the word count program. Give me a minute. Yes, let us go with this one, or Spark word count. You see this? This is what the word count program. You take Java or you take Scala, anything. This is what the word count program. Same word count program, you write it in MapReduce. Word count program in MapReduce. So this is not to degrade that MapReduce implementation is tough or something like. The thing that you need to understand here is, see here, this is what your word count MapReduce job, which you are already aware. I need not explain in this one. The same result of this MapReduce job can be achieved through these few lines of your Spark implementation. The beauty part here is your flat map, your reduce by key, these are abstracting the boilerplate code what you're seeing in the MapReduce part. Most of the time people say that writing code in Spark is easier. Yes, definitely easier. To the programmer, you need to learn the transformations and the actions, and you apply those things on your RDDs and you get your things done. But ultimately, when these transformations or your actions are getting executed in the background, the same Java code what I'm showing you in the MapReduce must be executed to get your things done. Not the same code, the similar level of code. You are only seeing the abstracted format in the form of transformations and actions here, but in the background you have the equivalent code running to get your things done. But it is been abstracted to the programmer level, which you need to understand. Maybe the code here looks to be very small, simple to apply to achieve the same task of word count compared to that of the MapReduce word count, but each transformation that you are seeing here, and finally you see the output is being your reduced by key is going to return me the counts, and that is being saved to the file what you specified. Then your word count implementation is being done with these 3 lines of code, not even 3 lines, 1 line. The actual thing is happening with this line only. This is to read the data and this is to write the data. But the actual activity of counting the number of words in the given data set is done only with this single line. But ultimately, this code is going to be drilled down to the extent of same MapReduce what you have seen, but that has been abstracted. That is the reason why I say the more you are strong in MapReduce, the easy it becomes for you to understand your Spark implementation, and you'll be able to get better visualization towards the Spark implementation. So I'm not making you to feel afraid, friends, here that you must go through the MapReduce to understand Spark, but your knowledge on MapReduce will give a different dimension when you look at your Spark implementation. And that's how I was able to adapt to Spark that easily, because I know the precise level at the very grassroots level execution of the MapReduce. I know what's happening. If I close my eyes, I can visualize how my MapReduce job getting executed in the background at the memory level. At each step, how things are happening, everything in my mind. So I can definitely and I can confidently say how my Spark programs are more efficient than MapReduce. Has been rightly asked by you, Ramji, in the beginning. This is what the strength you need to express in the interview, and that is how you are able to differentiate from the others. Yes,
Okay.
even even if they identify that you are not experienced, but they can identify that you have sufficient knowledge to work on any assignment because you know things from the grassroots level. That's how you can crack the interview. not with your experience. You claim
Okay.
10 years experience, but you're not able to convince the interviewer that you are skilled. You can never be in. You don't have any experience, but if you're able to create that confidence in the interviewer, yes, I can do it because I know in and out of everything what is a part of your Spark or MapReduce, anything. If the interviewer is confident that you are strong in one area, he can definitely provide you the time to upgrade your skill set on other things. And that's what the level of confidence you should exhibit in the interview. And that's the only way that you can go in. And you look at the thing. This is a kind of chicken egg problem. Which is first? Every client wants experience people, but who provides experience to the people? Someone needs to do, right? So even the client is clearly aware that even though you claim some experience, out of which everything may not be genuine, something definitely, but in your case, even if you don't have any experience, but if you are able to talk to the interviewer, like how I discussed in the today's session, you think you face any challenge to get in? What do you say, Ramji? Yeah, hi, you are there? Are you able to hear me, friends?